Hi everyone, in this video we're going to look at the idea of surface orientation. Before we do that, we'll just give you a brief introduction to two kinds of surfaces, orientable and non-orientable surfaces. So your orientable surfaces are your regular surfaces like a sphere or a cylinder or a rectangle, etc. Whereas a non-orientable surface is one of the most common ones, is called a Mobius strip. So what a Mobius strip is, you take a rectangle, you give it a twist, and you tie the ends, or you put the ends together. When you do that to a Mobius strip, when you do that to the rectangle, you get a shape called a Mobius strip. And the idea of a non-orientable is that this only has one surface or one side. Okay, so for example, when you have a rectangle, there's like a front and a back, right? So there's a front and there's a back. But for a Mobius strip, there is no front and a back. They are all one surface. So if you start walking along this, you will like go through the whole surface, the front and the back, without overlapping. Okay, so that's called a Mobius strip. And a Mobius strip is called non-orientable because if you take an arrow pointing up and you bring it back, it's not going to be pointing in the same direction, right? So it doesn't have a consistent orientation as you go through. Whereas orientable surfaces have a consistent orientation as you go through. But that's a more of a subjective description. Now we do need a more mathematical definition, and the mathematical definition is done, or is created using the idea of a unit normal vector. So basically we're looking at vectors that are normal or perpendicular to the surface, and we define the orientation of a surface given by z equals some function g of xy is given by the unit vector, which we will see in a moment in a much more familiar notation. And we get the square root of this is because to convert a vector into a unit vector, you need to divide by the magnitude, where this, you recall, is essentially your tangent vector divided by, or the cross product of the tangent vector divided by its magnitude. Which makes sense because how do you get a normal vector is you take cross product of two vectors in the plane, which in this case are the two tangent vectors. The surface integral of vector fields, therefore, whenever we are working with vector field, has a separate name which is called flux, and it's a name, or it's a word that you will see quite often in physics as well as your engineering courses. So what is this? So whenever you hear the word flux, it's saying it's a surface integral that we just learned, but instead of surface integral of a vector field of a scalar function, it's a surface integral of a vector field. So what's happening is we have the surface S and we have a vector field F given by rho v. And flux, what it measures is how much of it is passing through this particular surface. And in order to measure how much of it is passing through the particular surface, what we do is we take a small section and draw the normal vector n, and F is at some angle theta to it. So we look at the projection of F on n. So we project F in the n cap direction. Whenever we are projecting, it means we do a dot product. And that gives us the definition, which is if F is a continuous vector field defined on an orientable surface, so all of this is happening on an orientable surface. We will not deal with calculus of non-orientable surface. With the unit normal vector n cap, then the surface integral is the surface integral dot n cap ds. And this integral is also called the flux of f across S. Now this can be n cap we just saw is actually just a cross vector over here, right? So it's f dot divided by the magnitude of Ru cross Rv. Oh, sorry. If you dot product, then we don't need that. So we have f dot Ru cross Rv is going to be your surface integral, where your orientation is naturally defined by the Ru cross Rv vector. Okay, let's look at an example. Find the flux of this vector field zi, yj, xk across the unit sphere x squared plus y squared plus z squared. So before doing the math, what is it asking you? Remember, this is a vector field. What's a vector field? Look around your room. It's a bunch of arrows arranged around your room. The arrows have some direction at each point and some length. Now imagine a sphere. Now what we are asking is, when we find this flux is, we are asking how much of these arrows are going through the surface of the sphere, right? So depending on the length and the direction of the arrows, wherever you place a sphere will have a different sort of magnitude of surface integral of how much is going through. And so the result is going to be some addition of all the components of these arrows which are going through the surface. So we're taking the normal component of all of these arrows and adding them up, which is your surface integral of the vector field or the flux. So that's really what's happening here. So first of all, we need a parametrization. Because we are in a sphere scenario, we will use this parametrization, which is sine phi cosine theta, sine phi sine theta, and cosine phi, because r is 1. Once you have that, we will rewrite our vector function in the parametric vector field in the parametric form. So we have zi cap, which means cosine phi. We have yj cap, so this is sine phi sine theta, and xk cap, so sine phi cosine theta. Then we need r phi, which is so actually we found this r phi cos r theta in a previous problem. So from a previous result, we already have r phi cross r theta, and you can go through your notes and check for that. We obtained this as sine squared phi cosine theta, sine squared phi sine theta, and sine phi cosine phi. So once we have this, now we're all set, because what we need is a dot product of f with the r phi cross r theta. So we're taking this, copy, and dot product of this with oh, I think I messed up the phi here. It should be phi. Dot product of this. The dot product of this is going to be a constant. So multiply these two. What you have is cosine phi, cosine theta, sine squared phi, plus a sine cubed phi, and a sine squared theta, and a sine squared phi cosine, or a plus, sorry, cosine phi cosine theta. These are the same. So what we end up with is a double integral of 2 sine squared phi cosine theta plus sine cubed phi sine squared theta d phi d theta 0 to pi 0 to 2 pi. Now all of this can be broken down into a bunch of components. We have 2, 0 to pi sine squared phi cosine phi d phi, 0 to 2 pi cosine theta d theta, plus 0 to pi sine cube phi d phi, and 0 to 2 pi sine squared theta d theta. Okay, now this is 0 because you get sine theta, and then sine 2 pi and sine 0 are both 0. So this whole thing is 0. So we're left with this and this. This we know is given by pi, and this we have found previously using sine phi 1 minus cosine squared phi, and all of that, where the first part again becomes a 0, and then for the second part you use u equals cosine phi, so you get a u squared and divide by 3 and all of that, which gives you a 4/3 here, so eventually end up with a 4 pi over 3. So again, I'm skipping some of the steps here because we have seen these integrals several times before. And since they are always pretty much the same integral, you should be used to working with them. Now, is there anything special that happens when you work with surfaces of the form z equals gxy? Well, let's see. Because if I'm working with a surface of the form g equals xy, then I have PQR as my field, and my Rx cross Ry is negative del g over del x, negative del g over del y, and a 1, so that when I take this dot product, I'm left with a negative p del g over del x, a negative q del g over del y, plus an r dA. So it's not something that you have to remember, because you can find Rx, Ry. It's a little bit of work, maybe it takes a minute, minute and a half to get this result. And then you can dot it with PQR to get this form. Evaluate f dot ds, where the field is given by y comma x comma z, and S is the boundary of the solid region E enclosed by the paraboloid z equals 1 minus x squared minus y squared, and the plane z equals 0. So here we can use what we just saw, because this field is given by y, x, z, which act as p, q, r, although do not necessarily have to use the result. You can also do it step by step, which is dz over dx is negative 2x, dz over dy is negative 2y, right? So which means you have Rx cross Ry is negative dz over dx, negative, and a 1. So all you're really looking at is a dot product of y, x, z with 2x, 2y, 1. So that's 2xy, a 2xy, plus z, which is 4xy, plus what is z? Z is 1 minus x squared minus y squared. So you really have is a double integral of 1 plus 4xy minus x squared minus y squared dA. Convert this into polar. You get 1 plus 4 r squared cosine theta sine theta minus x squared plus y squared, which is r squared, r dr d theta, 0 to 1, 0 to 2 pi. So you have r minus r cubed plus 4r cubed cosine theta sine theta drd theta 0 to 1, 0 to 2 pi. Okay, so I'll leave this as video verification, complete the rest and email, or upload. Maybe at this point I'll change the instructions to submitting these things on Llama.Cuh for grading. That brings us to the end of this particular topic. Now we only have 2 ideas left to cover in this course, two results, which are generalizations of Green's theorem. And they're called Stokes' theorem and divergence theorem. And that's what the remaining videos are going to be about. So that's it for this video. Thanks everyone.